Okay. So welcome back, students. In the last video, we have seen the subsonic jet flow simulation for Mac number zero point 0.6. In this video, we will start doing the sonic underexpanded simulation in the same GAMBIT tool. And I'm having the file which is open for the last simulation. I have opened it again. You can see the same nozzle I am using. I am going to convert this mesh for simulating sonic underexpanded flows. So the same mesh boundary conditions are already given, but I will save this as Lowaraju sonic underexpanded. Right. So give accept. So I have changed the file name. So go to mesh command button. Go to face command button in mesh. You select the mesh, and before that you delete the previous mesh. We'll delete the previous mesh. Now go to mesh face, select, it is already selected in interval size. So now I am going to give a very fine mesh. So I will give interval size as 0.5. Just mesh it. You click on apply. It's a very fine mesh, so it will take time to mesh it. I think there is a problem. You interrupt that, close it. Better you delete the edge meshes. You select all the edge meshes, delete it. Now go to face mesh again, 0.5. Now you mesh. Yeah. So it has been meshed again with an interval size of 0.5. So please note the values. Now you can see mesh generated for phase 1 mesh faces. It is around 1 lakh. Mesh nodes are 1,76,590. Okay. So previously it will be very small grid. Now I have increased the size like anything. So save this again. Save. File, export mesh to as a 2D mesh, accept. So you can see mesh was successfully returned to Lowaraju sonic underexpanded. Now go to Fluent, file, read, mesh. So you will show the option discard case and data and read new mesh. You go to the second option, discard data, read mesh. You click that, continue. You click this, Lowaraju sonic underexpanded, click OK. Now I think everything is fine. Go to materials, everything is fine. We have already assigned everything. We will first scale this. Scale, use scale, close. Other things are same, density based solver, steady flow, axis symmetric, absolute. Check the grid, it is done. So it is grid is good. Display the grid if you want. You can see the grid display. Go to boundary condition. The only thing you have to change in pressure inlet is we are trying to do NPR3 here. I'll tell you what is NPR when the file is running. So we will give you NPR3 means it is absolute pressure. So gauge pressure we will give 2. Click OK. Go to solution initialization. Compute from inlet. You can see the velocity is around 400. You give initialize. You give run calculation. Before this, go to solution controls. Reduce the Courant number to 1. because it will diverge if you give 5. So go to run, give calculate, it will take time. So meanwhile, I will tell you what do you mean by under expansion. For that, you see the same paper. For example, if you want to understand the under expansion case, go to sonic under expanded. So you can see, I will give you a book, recommend a book like Applied Gas Dynamics by Dr. E. Radhakrishnan, retired professor from IIT Kanpur. I am opening that book. I will tell you the flow physics about the sonic under expansion. Naren AD2 Applied Gas Dynamics. Chapter 12 is jets. So in this chapter, he has clearly given what is under expanded, what is over expanded, and what is correctly expanded. So we will just see that under expanded case alone for your understanding. This is over expanded. This is correctly expanded. You can see under expanded. So there are different cases in under expansion itself: moderately under expanded jet, highly under expanded jet. Okay. So now you can see, you can compare this. Moderately under expanded is nothing but, for example, to be very precise, if you see, as per isentropic relation table, isentropic relations, you have this, you go to isentropic relations. Isentropic relation calculator is there. So you can see this is isentropic flow, isentropic relation calculator is there. I will show you that formula. It is there. Okay, this formula. The morning I have told you, right? PT by, this is ulta formula. PT by PS is equal to 1 plus gamma minus 1 by 2 m square power gamma by gamma minus 1. This minus is given because this LHS is ulta. Okay. So in this, I have told you, if you substitute any Mach number, you will get the pressure. So if you substitute Mach 1, you will get 1.89 or 1.9. So what if you exceed this 1.9 pressure in subsonic flow? Here you can see a CD nozzle. What if you increase this pressure beyond 1.9? What will happen? In a convergent nozzle, choking will be happening. So because of the choking, your jet will become sonic under expanded, because Mach number will be 1, it will not go beyond 1. To make it go beyond Mach 1, you need a convergent and divergent, like it's shown here. So if you want in a convergent duct, if you go beyond 1.9, it will become sonic under expanded. So the properties are given here in this book. So this is, so we are now currently running NPR3. NPR3 means that PT by P naught is 3. This PT by P naught is, or P naught by PS is 3. Okay. So that is sonic under expanded case. So that comes under moderately under expanded, low. Okay. So what will happen? See, at the nozzle exit, the exit pressure will be 1, but your nozzle exit pressure is 3, which means pressure is more. Pressure has to be reduced. So to reduce pressure, you know, A shock will reduce the pressure, right? See, if you have a shock, if you have a shock, I will draw a shock. So this is shock. Okay, I already told you this is a normal shock. Say this is a normal shock. Here, pressure, temperature, velocity, and density. So across a shock, pressure will increase, temperature will density will increase, but velocity will decrease. So I am talking about total pressure here, which means stagnation pressure. Okay. So stagnation pressure, velocity should decrease. So to decrease the velocity, shock will be forming. So you have a series of shock here. This because of the series of shock, series of oblique shocks. You can see, I will zoom this. Okay. So this is a series of shocks. It is originating at the nozzle tip and it is getting reflected back. Okay. This is called incident shock. You can see the mouse pointer. This is called incident shock. This is called reflected shock. Incident, reflected. Again incidence, reflected. Like that it is going on. Okay. So if you see, this is the jet boundary. It will reflect along the jet boundary. Or you can consider this as a potential core. So in the sonic underexpanded potential core, your shocks will reflect. So that is what it is given in the book also. You see in underexpanded, jet is said to be underexpanded when the nozzle pressure is higher than the back pressure. Since the nozzle exit pressure is higher than the back pressure, wedge-shaped expansion waves occur at the edge of the nozzle. Okay. So what will happen? See, nozzle exit pressure is higher than the back pressure means what? This exit pressure. Exit pressure, back pressure means atmospheric pressure. So PE is greater than, we will write it. PE where should I write? Or I will take a new. Okay. Tell me. PE is greater than PA. Atmospheric or back are same. So these since the nozzle exit pressure is higher than the back pressure, okay, expansion waves, see I already told you about expansion waves. Expansion waves occur at the edge of the nozzle. So what the expansion waves are the opposite of a shock wave. Same properties, you see the properties. Pressure is increasing in a shock wave, velocity is reducing in a shock wave. In converse, in an expansion wave, pressure will decrease, velocity will increase. So that exit pressure is atmospheric 1, NPR 1. Nozzle exit pressure is NPR 3. So I have to reduce the pressure. So you see there are a series of, this is expansion wave. I have told it is shock wave, it's not shock wave. This is expansion fan, and particularly this expansion fan occurs because your nozzle shape is like normally if you see an expansion fan, it will look like this only. A fan, if you see, if you have a like this sudden, so your flow is, if your flow is like this, if your flow is like this, you will have an expansion fan here. This is called as an expansion fan. So here, if your pressure is more, after the expansion fan, your pressure will less. This is a ramp. Like the flow area is more. If you see this nozzle, this flow area is also more. See, it is contracted here. Flow is contracted here. Suddenly, there is a free space. So the flow area is more. So you see here, this is like an expansion ramp. I will make it here. See, this is like an expansion ramp, right? You can visualize this as an expansion ramp. Since there is an expansion ramp, you have an expansion fan. Similarly here also. Clear? So this expansion fan has been reflected like this, and then totally you will have this, like we will see. We will continue the story. There is a series of waves. So these waves cross one another and reflected from the boundaries of the jet flow field as, so this reflects as a compression waves. This expansion fan reflects as a compression waves. Okay, that you can see here. Okay, and then again crosses one another and are reflected on the boundaries of the jet as expansion. So this process is continuing. First expansion fan will form, it will reflect as compression wave, again expansion wave. Compression wave is nothing but a shock wave. So this process is continuing. So this figure shows the sketch of expansion jet. For underexpanded jet, in addition to the expansion fan caused by the level of underexpansion, there will be another expansion effect due to the relaxation experienced by the jet on exiting the nozzle into a large space. That I told you, this is a confined space, this is a large space. So that relaxation effect is also there. So this combined effect of these two causes a stronger expansion fan than what expansion level alone can establish. This essential difference between the moderately underexpanded and highly underexpanded jet is that at the end of the first shock cell, there is no MAC disk in the former. So in moderately underexpanded, there is no MAC disk, but here you will have a MAC disk. Can I show you MAC disk here? If you see in the paper, see this is moderately underexpanded, this without co-flow. This is moderately underexpanded. NPR 3, we are doing NPR 3. So there is no MAC disk. But NPR 5 and NPR 7, you can see there is MAC disk. You can see my pointer. This is called MAC disk. You can see this also. This will look like a disk. Okay. See, she has shown the MAC disk here. Similar disk is here, right? So at moderately underexpanded or low underexpansion, the disk will not come, rather than shock crossover will come. These are shadow graph pictures, experimentally obtained shadow graph pictures. Okay, so this is the flow phenomena of underexpansion. So now we will go to some divergence has happened. So what we will do, we will run with some We'll do check case. So first order solver we can change to second order. You can see solution methods. See first order upwind we can change into second order, and then we can run. Maybe solution controls we will drop it to 0.5. Initialize again from inlet, discard, run calculation. We will run it again, and then after the run we will do the post processing. Now we will end the video by clicking the run calculation again. Let it run. We will again continue the video after the solution has been converged. Okay? Any doubts? Thank you.